Hello again. So now let's continue on with our interpretations of the derivative. We've discussed how the derivative is a tangent and how we can use that to find where a function is increasing or decreasing. Another big idea is that the derivative is a measure of the instantaneous rate of change of a function. Now that's really just another funky way of saying slope, but if we think of the function of x, then f of x measures the instantaneous rate of change of the function. And since this is a limit of the average rate of change, the slope of a secant line, then the units of f prime of x are the same as the units of that slope, which is the units of output divided by the unit of input. Same as how we interpreted slope back in an algebra course. So, for example, let's suppose that we have a function v of x, and v of x measures the volume in decibels in a room x minutes after a party starts. Then we're given this information. We're told v of f is 70, v prime of f is 2. What do we know? I'd like for you to pause and try and answer these on your own before I answer them. Alright, so here's what we know. X is in minutes, and x is the input of the function. V is the output of the function. V is the output, and measures the volume in decibels. Okay, V is the output and is the volume. Alright, so the statement, V of 5 is 70. This is telling us that 5 minutes after the party starts, that was the input. 5 minutes after the party starts. What's the output? The volume the room is 70 decibels. Now, that's not new. You should have been able to do that from any algebra course. Interpreting a function given an input and an output, you should have been able to do that from any algebra course. Here's the new idea. V prime of 5 is 2. V prime of 5 is 2. Alright, again, 5 minutes after the party starts. That's still the input. What do we see? V prime, the derivative, is positive 2. The derivative is positive. Hey, from what we've seen already, that means that the function, the original function, is increasing. So that's telling me that the volume in the room is increasing by 2. Now, how do we use the 2? 2 what? Units of output per unit of input. It's a slope. Slope has units, units of output divided by unit of input. So then, at 5 minutes after the party starts, the volume in the room is increasing by 2 decibels per minute. Unit of output over unit of input, 2 decibels per minute. If, for example, let me just make something up, what if it had said instead that v prime of 5 was negative 2? How does that change things? So now the statement would be the same. 5 minutes after the party starts, the volume of the room is decreasing by 2 decibels per minute. That would be the only change. So if the derivative is positive, the original function, the output, is increasing. If the derivative is negative, the original function output is decreasing. Let's see another example. A little tougher here. Oil is spilling on a surface such that the area of the oil slick is given by A of t is 6t squared, where A is measured in square feet and t is measured in hours. Find and interpret A of 10 and A prime of 10. This is similar to the previous exercise, but here they don't give us the numbers. They don't give us the outputs for A of 10 and A prime of 10. We have to find them given the function. And we'll also have to find the derivative of the function to answer the second part. So now would be a great time to pause and try this out on your own. Alright, so first, A of 10. Well, that's simple enough. We can just use some algebra here. A of 10 would be 6 by 10 squared. That's 600. So, now let's understand. A is measured in square feet, and t is measured in hours. Alright, so my interpretation. After 10 hours, the oil slick has area 600 square feet. Alright, that was easy enough. Now we're also asked to find and interpret A prime of 10. Well, we don't know what A prime is, so let's calculate it. A prime of t would be the limit with h approaching 0 of A of t plus h. That would be 6 by t plus h squared minus A of t, which would be 6t squared over h. Let's expand, distribute. So let's see, that would be t plus h squared. That's t squared plus 2th plus h squared times 6. That's 6t squared plus 12th plus 6h squared minus 6t squared divided by h. We see that the 6t squares go to 0, right? We have the like terms. Those go to 0. The remaining terms have a factor of h. This is the limit with h approaching 0 of h by 12t plus 6h over h, which is the limit with h approaching 0, removing the factor of h of 12t plus 6h. Now letting h approach 0, the second term goes to 0, and so then A prime of t is then simply 12t. So what is that telling us? Well, if A prime of t is 12t, then A prime of 10 would be 12 times 10, which is 120. Now interpreting that, after 10 hours, the area of the oil slick is increasing, again, because 120 is a positive number. That means the function is increasing at that point. The area of the oil slick is increasing by 120 square feet per power. All right, so there's a couple examples of how we can, if we're given a physical situation with a function, how we can interpret the derivative in context. All right, now we've talked about motion, we've talked about a position function and how to find an average velocity and how to find an instantaneous velocity. And in fact, we saw that that concept was exactly the derivative. And so what we've seen that the velocity is the instantaneous rate of change of the position. Velocity is the instantaneous rate of change of the position. In other words, if s is a function, then s prime of t is the velocity of the function. So what that's saying is, right, the velocity function v of t is s prime of t. Now, it also turns out that if we use a similar process, but starting with the velocity function, we find an average acceleration, and then it becomes an instantaneous acceleration. The instantaneous rate of change of the velocity of an object is called the acceleration of the object. In other words, if v of t is a velocity function of an object, then v prime of t is the acceleration of the object. So a of t, the acceleration, is equal to v prime of t. So the derivative of the position function is the acceleration function. Well, what is the, wait, the derivative of the derivative. Can we do that? Are we allowed to find higher derivatives? Sure. We find the derivative, it gives us a function, then we can usually, depending on this idea of differentiability, we can find the derivative again. So here's what we're saying. We're saying that the acceleration function, a of t, is the derivative of the derivative. So that would be s prime of t. And we can have what are called higher derivatives. Okay, so this is a second derivative of the function. So a little bit of notation we need to be aware of. If we're talking about a general function, right, we're given some f of x. We've said that the derivative with respect to x of f of x can be written as f prime of x. And then if we go through this process again, d by dx of f prime of x, if we differentiate with respect to x the function f prime of x, we get a second derivative, f double prime of x. And we can continue this process. We can find even higher derivatives. If we differentiate with respect to x, f prime prime, f double prime of x, we get a third derivative, f prime 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 of x. Now beyond that, we're getting a lot of little apostrophes up there. We're getting a lot of primes. So beyond that point, if we wanted to talk about the fourth derivative, we would use the notation f, and then instead of drawing 4 primes, instead of drawing the 4 apostrophes, we would put a 4 in parentheses in the superscript. So I'd write f4 of x. Now, the parentheses are important. If I don't write the parentheses, that means I'm finding the function f of x raised to the 4th power. That means something different to me. So that's how we generally write a higher derivative. And if we wanted to talk about the nth derivative of a function, where n is some whole number, let's just talk about whole number derivatives, then we can write f and n in parentheses in the superscript of x. Another notation for this, if we wanted to talk about the nth derivative, instead of f nth derivative of x, using that notation, an alternative notation for the nth derivative that we should be aware of is we would write dn over dx to the n of f of x. So notice if it was the first derivative, it would be d1 over dx to the first. And we would normally not write the ones in that situation, but we could. It's just not normally done. But for higher derivatives, right, so an alternative notation for the second derivative, what we mean by this is, if we wanted the second derivative using the alternate notation, that would be d square dx square of f of x. That's a second derivative, which is equivalent to f double prime of x. Those mean the same thing to me. Okay, so some notation to be aware of here. Alright, so for example, if f of x is 6x squared, find f prime of x, sorry, not f prime, f prime prime, the second derivative of x. Alright, so what I would do for this, start by finding the first derivative, using what we've seen before, a limit definition. Then, using that as the new function, calculate the derivative again. So, doing this at this point in the course, you would have to use two limit processes. Now would be a good time to pause and try this on your own. Alright, so if f of x is 6x squared, then f prime of x would be the limit with h approaching 0 of f of x plus h, 6 by x plus h square minus f of x, 6x squared, over h. This would be the limit with h approaching 0 of 6x squared plus 12xh plus 6h squared minus 6x squared over h. We combine the like terms, we factor out the h. This is the limit with h approaching 0 of h by 12x plus 6h. This is the limit with h approaching 0 of 12x plus 6h. Then letting h approach 0, this becomes 12x. F prime of x is 12x. But we're not done. We want the second derivative. So then the second derivative, f double prime of x, would be the limit as h approaches 0 of f prime of x plus h minus f prime of x over h. And so that would be the limit with h approaching 0 of 12 by x plus h minus 12 by x over h. Limit h approaching 0 of 12x plus 12h minus 12x over h. We remove the, we see the like terms of 12x minus 12x, that's 0. And so we're left that f prime of x, double prime of x, sorry, is the limit as h approaches 0 of 12h over h. So that's the limit with h approaching 0 of just 12. Right, removing the common factor of h. That leaves us with just 12. So then that tells us that the second derivative, that f double prime of x, is exactly 12. So we can calculate a second derivative by finding the derivative of the derivative. So lastly, let's talk about differentiability. I've mentioned it a couple of times, but haven't really gone into what it means. So if we remember that we've defined the derivative as a limit, then that gives us some ideas of where a function may not be differentiable, because that limit must exist. All right, so if we think about this, back a couple topics ago, we said that f prime at a was the limit with h approaching 0 of f of a plus h minus f of a over h, right? We defined that as a limit. And so if we think about it, where might a limit not exist? Where might a limit not exist? So if we think back of where limits may not exist, there's a few different possibilities. One, so again, when will this not exist? We get a few different possibilities. One, if the left limit and the right limit are not equal. That would be one possibility, right? So if the left limit and the right limit were not the same number, then that limit does not exist. We know that if there is, and we also know that if this limit is infinite, we have an infinite limit, then we've said that officially that limit does not exist, but we called it infinity. Those were the two big situations where the limit did not exist. So graphically, what this tells us is there's a few situations where we might expect the derivative to not exist. The first big situation is if the curve has a corner or cusp. So for example, if we had a curve that did something like this, where here's the a value. Notice that if we looked at the derivative, if we looked at the slopes on the left of a would be positive, and the slopes on the right of a would be negative, and there would be an immediate change from left to right. This would be a situation where f prime of a does not exist. Another shape, that's what we mean by a corner. There's a sharp change in the derivative, in the slopes to the left and right of a. Another situation that's similar is if we have what's called a cusp. A cusp might look something like this. We have a curve that does something like this, and then that. This shape right here, where again, here's the a value, this shape is called a cusp. Right? This is a corner, and this shape is a cusp. A second situation that causes causes would be if there's discontinuities, specific kinds of discontinuities, right? If you have a jump or an infinite discontinuity. So a graph with a jump discontinuity might look something like this. There, here's A, and we have maybe an open point here, and here's a closed point, and the curve does something there. Okay. Here we have this jump discontinuity. The derivative would not exist at A. An infinite discontinuity. Alright, so that might be a curve that has a vertical asymptote at A. So here's A, and if we had some sort of a vertical asymptote, maybe the curve does something like this, and then like this. Again, the derivative would not exist at A. Because again, that limit, that special limit, would not be the same on the left-hand side and the right-hand side for the jump discontinuity. And then for the infinite discontinuity, the slope would become infinite. And officially, that's a does not exist situation for the slope. Then the last situation that we need to be aware of is that if the curve has what's called a vertical tangent. And so we will sometimes see curves that do this. So for example, if we had a curve that looked something like this, let's say it looks like this, and then like that. And here's the A value, right? So I'm not going to put the mark on the x-axis, but there's the A value. So notice what's happening near x equals A. The slope is positive, right? And the slope is getting very large. And at this point right here, the slope is becoming vertical. All right, and we actually see this. This is a common feature in the curve. This is just a transformation of the cube root function. So here, this might be the function f of x is the cube root of x minus a. If you were to graph that function, this function has a vertical tangent at x equals a. Its derivative does not exist at x equals a. And we can see other curves, like for example, this first curve up here in the top left, this is a transformation of an absolute value function. This one's a little trickier. This a cusp feature happens with certain graphs. If you graph like x to the 2/3, if it's graphed correctly by your calculator, you'll get a cusp. But here, like this graph here, that's an absolute value function, absolute x. Or some transformation of that will have a corner. Cusp, x to the 2/3 will have a cusp. Jump discontinuities, these are, our sort of standard functions don't have jump discontinuities. But we've certainly seen infinite discontinuities. A simple function like f of x equals 1 over x has an infinite discontinuity. So there are some fairly basic functions that have derivatives that don't exist at certain points. And we're going to learn in later sections how to find those points, and we need to be careful about them. Alright, so that concludes this topic. I hope you've learned something about how to interpret derivatives. Alright, I'll see you in the next topic.